Recording in progress.
Good morning. Today I'll start off with returning to fatigue, which is the dominant cause of failure in mechanical engineering. We'll get back to that and the Moore test specimen. And after about an hour, or after the break, I'll go through test 2, which will be available for you to pick up today from 2 to 6 and after 10 tomorrow morning. Okay. And I'll go through the solution to make some comments. But this fatigue, I did this very crude thing where I bent a paper clip and through an angle phi or delta phi. And you can do some of these demos. I'm not sure how well, or perhaps I'm not sure how poorly they're getting transmitted in this medium. Probably my lack of skill with using the medium, but you can do these things yourself, and you'll find that you get something that looks a bit like this. When it ends the number of cycles to failure, and delta phi, as delta phi goes up, you get something like this. Okay, that's what we got. The other thing when you do these tests, if you do it a couple of times, you realize that there's quite a variation in end, that there's quite a lot of scatter in this data, and we'll talk some more about that. This is all these ends here were just a few cycles. This is all low cycle, and really for this metal, let's assume it's a steel. This stress strain curve, not drawn to scale, looks a bit like this, okay? And delta phi is epsilon. They can be along here, okay? But the changes in the stress are very small. So if we did this versus, this would look more like this, okay? We're going to do that with a Moore test specimen, and we'll see, okay? It won't be like this when you do it versus stress. So then we started doing this Moore test specimen. What it looked like. So you have a shaft. And it's rotating. Supported on a couple of self-aligning bearings. These self-aligning bearings will let the thing rotate locally, but keep its deflection here 0. Then we put a weight in the central section. It's hanging from cords on a pan. And here's the weight. The whole device is symmetric, so if the length of the pan is L, the length in from the two bearings is lowercase l on both sides. Then if you look in on the shaft, at position 1, it could be a minus sigma B max. At 2, that's on a neutral axis. At 3, now it's on the bottom, it's in tension. And at 4, it's got back to the neutral axis. So as it rotates, it goes through these 4 stress states, and so it's got an alternating stress. So it started off here. Then it went to there. Then it went to plus sigma B max. There's a given point on the shaft now, moving around here. This is what it's experiencing, and back to 0, and so on. Okay. And this is a test specimen, but this is exactly what happens in practice in mechanical engineering. If you put a torque on this thing here, that'll be constant. Okay. Now, you could vary the torque as you load it up and load it down. There'd be a few variations. These variations go 1 per revolution. You can have thousands of revolutions. So you've got far more cycles in bending than you do have in torsion. Okay. And so this is the dominant thing that breaks specimens. And so what we need to do to analyze this test more is we need to know what sigma B max is. Okay. Are there any questions on that? Okay. So every time it rotates, this part starts off the top, moves to the side, moves to the bottom, round. In 1 revolution, it sees this oscillation between minus sigma B max and plus sigma B max. And you can have 1,000 revs per minute. And so I've seen lots of these cycles. In order to understand this test, we need to get what sigma B max is. If I do a free body, it's very simple. It's symmetric. This is the shaft. And so it's fair to say half of the weight is coming through each of the strings. It won't be perfectly true in practice, but it'll be close. And that's opposed by 2 reactions. And since it's symmetric, they'll be equal, so they'll be W upon 2 too. When you draw this thing, you could have put reactions in here and done the statics to get it, but this is a fairly simple symmetric problem. We have the geometry over here. In a free body diagram, you can put the geometry in, but if you're right next to the configuration statement and it's got the geometry, you don't need to put it in. And it's slightly quicker not to, but nonetheless, a more complete diagram would put in these lengths here. Now we need to get the bending moment. Well, it's fairly straightforward. We're going to measure X from that end. put in the known reaction. Then I put in the shear force, positive, reducing a clockwise movement. It doesn't matter anyway. Then I put the bending moment, compressing the top, the standard convention. If I take moments about here, I get that M, the moment that way, is equal to the moment in the opposite direction, which is W x upon 2. If I get to the central section, in addition to the reaction W upon 2 here, I'll have the load. This distance here is L. So now X is greater than L. This would be the correct moment for X less than L. Again, I put these in according to the positive sign conventions. So as I've told you, there's almost no need to work out the shear force. I take moments about here. M's the moment that way, it's equal to the sum of the moments clockwise, which will be W upon 2 times X. But now it's going to be opposed by minus W upon 2, and its moment arm is X minus L. So these two cancel. I get WL upon 2. So the bending moment diagram looks like this. It's linear. It's linear from 0 to L, increasing, and it gets up to this value of WL upon 2. And it stays constant at that value, then it's symmetrical, just drops back down. So this creates sigma max. And M max is just WL upon 2. So this will go down to 16. Okay, well now we're going to generate some data. What we do in these tests is we vary the weight W and then count the number of cycles to failure. Once we've got a certain N, then the stress, the maximum bending stress that produces that failure, it becomes the strength. We're going to denote that by S. We use S for strengths as opposed to sigma for stresses. So S is, and throughout this course, S is always measured stresses when something happens. In this case, it's going to be sigma B max for N cycles. With a given material. end cycles to failure. Perhaps I should have put that. Let me fix that. Let me reiterate. And this is what the data looks like for steels. Most of the testing that's been done, fatigue testing over the years, is for steels. There's quite a lot of testing for aluminum. There's also testing for basically every other metal that's used. But we'll deal with steels to start with. It's going to turn out that there's a wide variety of N. N varies by orders of magnitude. I don't know if you remember this, but up to 10 to the 3 or 1,000 cycles we call it low cycle, and above 10 to the 4 we call it high cycle, and between 1,000 and 10,000 is somewhat debatable. Some people call it transition. We're going to lump it in with high cycle. And after you start getting to 1 million cycles, it's pretty standard in steel to regard that as indefinite life. Okay? Whether that's really the case or not, we'll discuss a bit more later, but quite often that is the case. So since we have this huge variation in the number of cycles, we're going to take logs so we can put it all on one graph. And it's going to be convenient to also take logs of S. Okay. So on this thing here, we're going to plot log. Now we could take log of S. Well, the argument of a log function should really be dimensionless. So we're going to normalize by the ultimate strength. And at the very top here, this will be 1. So this will be 0. And then as this goes down, this will be log of a number less than 1. So this will decrease. So on this scale here, and that's about all we need. Okay. And along this axis here, we're going to take log of n. N is just is a dimensionless number. And this is what the data looks like. The general trend you'd expect is down like this. Okay? As I tried to show you with the paper clips, during the low cycle, which is what the paper clips were, the stresses are rather compressed. They don't vary that much. And so it's actually kind of flat. Okay. That's the 10 to the 3. This is low cycle. When we get to 10 to the 6, we drop off more rapidly. And then after this, we regard this as indefinite life. And I'll explain a little bit more what that phrase means. Simply put, it's quite possible you don't have to worry about fatigue failure. There's this little debate whether this is really high cycle or not. We just lump them together because when you reduce the data, the curve fit that works from here to here also works reasonably well here on a log-log plot. The book discusses this data reduction scheme in some detail more than I have, okay? But this is basically what you end up with. So let me go through and highlight some of the points on this data fit. Well, this point here, that's log of SU of ASU, which is log of 1, which is 0. Okay. The corresponding point here we're going to say n equals 1. It's questionable whether it really gets all the way up to 1. If you put the load on to the ultimate stress, you might not get to rotate it once, but we're going to approximate it as 1. And so we'll have a log of n equals 0 to. So these two, this is the y-axis for this point, and this is the x-axis. This point here at point 2, it turns out that you just reduce the stress to the ultimate stress to by 5%, sorry, by 10% from the ultimate stress. So here we have S of ASU is 0.9. No prime there. I'm getting this point here. Okay. And log of 0.9 to the base 10 is minus 0.05.
For the first point, should that be log of S over SU?
The first point here, that S is equal to SU. Yes.
Oh, okay, thank you.
Yeah, I should have written that. That would have been clearer. Okay. So S is equal to SU. So you get log of 1. Okay. Yeah, could have made that more clear. So that's point 2 here. Okay. Whereas 2 prime here is log n to log 10 to the 3. That's the end of our low cycle region. I don't know if you remember this, but when you have a power of a log, you put the power down front, that's 3 log 10, and log 10 is 1. So that's 3. Okay. We can also get this point here. For now, I'm going to say what happens here, you get to the end of your high cycle when S, let me put that, that's what I should have done up here. Is equal to Sn. Sn is the strength for indefinite life, and it's approximately equal to, so in terms of what this point is, it's log So log of 0.5 to the base 10 is minus 0.3. The corresponding point here is 10 to the 6th cycles. And so log of n is log of 10 to the 6th, bring down the 6th is 6. And this is really why we use for the base 10, we get integer numbers along here. You could do a log-log plot in natural logs, but then you wouldn't have a nice integer numbers along here. On this axis, there's no advantage one way or the other. Okay, and so that there's a lot of scatter about this data. And we'll talk a bit more about that later, but there's quite a lot of scatter. When you plot it on a log-log plot, it doesn't look too bad, okay? But these are logs that are varying. And so small variations here can be a factor of 2. Okay. Well, now I'm going to fit the data. I'm going to fit the data from here to here. We've got a straight line through here, which is sort of the mean value, and we'll do that. I'm going to call this point here Sn when I do this fit. And we might substitute 0.5 SU, which I had on the plot later on. Now, most steels conform to this, okay, on average, okay, not individual stress tests, but the average stress tests tend to conform reasonably well to this. And in terms of what you're going to use in the class, this is what we're going to use. So let me do the high cycle. So I'm going to take y, my y-axis, be log of S upon SU, and my x-axis be log of n. Then I have a couple of points. I could call this y1, x1, or x1, y1, and this one here, x2, y2. An equation of a straight line from that looks like this. Y minus y1, x minus x1 equals y2 minus y1 over x2 minus x1. Y1, well, I said this is 0.9, it's log of 0.9, which is minus 0.05. We'll just use the log right now. X1, I already pointed this out, is log of 10 to the 3 is 3. Y2 is log of Sn over Su. So I'm calling this point Sn. We may often approximate it as 0.5 Su. But X2 is log of 10 to the 6th, which is 6. So I put this together, it looks the following. This is y, log of S over Su, minus log of 0.9 divided by log of n, which is x, minus x1, which is 3. And that's going to equal y2 log of Sn minus Su minus y1, again, minus this log of 0.9 over x2, which is 6, minus x1, which is 3. And what we want to do here, when you've got this log fits, is you want to make this side the log of something, one thing, and this side the log of something else. Then if this is log of alpha and this is log of beta, then log alpha equals beta. And to do that, we have to combine logs. And I know you've had these laws of logs, but let me just remind you how they work. So if I have log of A minus log of B, that's log of A divided by B. So here I'll be able to subtract that and I'll just put the 0.9 down the bottom. On the other hand, if I had log of A plus log of B, that's log of A times B. Okay. And eventually we're going to get to things like n log A, that's log of A to the n. If you have some coefficient of the log, it's the same as the argument of the log raised to that power. So let me use these laws to simplify this. So this will be log minus there. So I divide, so it's S. Let me multiply across by this. This is just 3. So I simplify this side too. This is just 1/3. Again, this is the difference. So I divide by that. Sorry, SU. Times this. I really want to get this in, okay? If I look at this minus 3 times 1/3, that's minus 1. I put it on this side, it's going to be plus, okay? So if I had log of this plus log of this, that's the log of the product. And I've taken care of that. Now I've got this log of n, and I've got this thing here, which is like a coefficient, a messy coefficient, but still that's what it is. I get that. Now I've got log of alpha equals log of beta, so the two are equal. Well, I really typically want to get in. So if I have n raised to the power m, if I take 1 upon m of this, that'll get rid of the m here. So I just take the reciprocal. So that'll give me the following. This thing raised to the reciprocal power, to the power, which is the reciprocal of this number. The reciprocal of the third is 3. And then I want the reciprocal of this, so I divide by it. So if you give me a bending moment and I get the stress, if I've got the endurance limit measured from some other test and the ultimate strength measured from some other test, then I can tell you the life, okay? we can simplify this. Oftentimes, you're not going to have a measured endurance limit. The standard approximation for SN, the strength for indefinite life, is half of the ultimate strength. Okay, that's the standard approximation. For some years, we used to use a fraction of the yield strength. We found the ultimate strength. This thing here was a better approximation because different heat treatments changed the yield strength significantly, and so you had to keep changing the coefficient. And so this is the standard thing used in practice. If you put this into this, you'll get 0.5 divided by 0.81. So I've substituted for SN, and that cancelled one of the SUs, but not the other one. And this is 3 divided by 0.5 over 0.9, the log thereof. So under this approximation, we get a relatively simple expression. When you've got SN, you want to use this. This is more accurate, okay? But SN takes quite a while to test and get to it. So quite often we don't have it, in which case you can use that. Now that's all just using logs, and if you haven't seen it for a while, it may look a little peculiar, but this is how you do data reduction. Let me do another one. Let me do low cycle. I'm going to fit this from here to here, okay?
Dr. Sinclair?
Yep.
Is that 3 over log to the SN over 0.9?
Yes, sorry. It's not very clearly written. Yes, sorry.
All right. Just want to make sure. Thank you.
Yeah. That's okay. Huh. I don't know how much clearer that is. Okay. So this minus 11.75 is 3 divided by log of 0.5 over 0.9. And that's a log of 0.5 recurring, which is minus about a quarter. It's just a bit under a quarter. So when I take reciprocal, I get a number just a bit under 4 multiplied by 3, I get minus 11.75. Now Y1 at the start of this fit is here. So Y1 was log of SU over SU, so Y1 is 0. And the number of cycles was log of 1, so X1 is 0. In the very first part of it. And this one here was back to Y2. Y2 is 90% of S, S was 90% of SU, so it's log of 0.5. And that got us 10 to the 3 cycles. Okay. So Y2X2 used to be Y1X1 in the previous fit. Then what I'm going to have here is log S over SU, that's what Y continues to be. Y1 was 0. X is log of N equals log of Y2 minus Y1, which is 0, over 3. So it's relatively simple fit. It'll be log of n with this thing as a coefficient. So this becomes to the power. Then this thing here must equal this. It's more customary to go and get n in terms of, you could actually use this formula for given a certain cycle life. This will tell you what S is. It's common to use these things to estimate life for a given S. In which case, I whatever this power is here, I take the reciprocal of it, which gets rid of it here and put it over here. And we can calculate that. Log of 0.9 is about minus 0.05. So it's going to be about minus 60. It's not quite minus 0.05. So that's the low cycle life estimate. Now, we're going to talk some more about scatter. There's a lot of scatter here. You want to be careful when you start using exponents. Okay, I'm going to give you exponents to 4 figures. That's good practice in engineering. You start messing with these things, you'll get very different answers quite quickly. Okay, so exponents to 4 figures is reasonably safe. You won't have any significant calculation errors. Okay. The same thing for this. Exponents. It's probably not so necessary to have 4 figures there, it's just kind of consistent. But these ends, the number of cycles, are really only going to be good to 2 figures. Okay. It's just that if you're changing this, you'll change those 2 figures. Let me do an example. So even though it's a test specimen, the lives you get here apply in practice because often shafts are under bending more often than not. And so if they're steel shafts, you can start using what we've got to estimate life. Here's an example. I'm going to show you how life varies with load for steel. I'm going to give you some specs for a Moore specimen, but that's not to say you couldn't have something very similar to this in a shaft in practice. So the diameter of the shaft is 0.3 inch. If you remember the formula for the maximum stress, it was W little L, so we need to know what little L is. We don't need to know what big L is, although it's typically not less than 1 inch, but little L is 2 inches. We're going to have a high strength steel. It might be something like 1045 in a hot rolled condition or something like that. This is a reasonably high strength, not common construction steel. Then I'm going to ask the question, we're going to have 2 loads, 180 pounds force, and W2 is 90% of W1, which is 162 pounds force. So I'm going to ask the question of what's going to happen to the life when you drop the load by 10%. Well, the basic approach here is we'll go calculate sigma max. And once we get sigma max, okay, for these different loads, that'll become the S, and that'll tell us which region we're in. So when you do these life estimates, you have to decide which of these formulas you're going to use, and there are three. You could be in any of three regions. We have another calculation yet, we'll find out. If these two loads do not have indefinite life, there'll be no change. Okay, it'll just be indifferent. There'll be changes if it's in this region. The other thing we're going to do is we're not given SN. So the standard thing we do is we're going to take SN as SU divided by 2. And that's what you do automatically. Well, if we do the higher weight, we'll see if it's in high cycle, this must be high or indefinite. Okay, it's got a lower load. Okay. So sigma B max, 16 WL from pi d cubed. And 80 L is 2 inches. This will come out in PSI. $67.9 KSI, 67,900 PSI. I've divided by 3. Well, the high cycle starts at it starts at 0.9, and with this assumption that SN is SU, it becomes a definite 0.5, so that's in the range 90 to 50. So this is in this range. When we drop this by 10%, it's still going to be in this range. Okay, and so it'll be 61, so it'll still be in this range. So both parts are going to be indefinite life. So now we can go estimate the life. Well, for high cycle life, we had this when under the assumption of this. You could 3 figures would be enough here. Oh, sorry. This is where I recommend 4 figures the exponent. So I've dropped the figure there. So this is a small number, or a number less than 1, and you raise it to a high power, you get a very small number. And the minus sign means you take the reciprocal of that. So this number here, point 679, 0.617, 0.419, less than a half. So it gets very small, and then you take reciprocal and you get 28,000 cycles. Let me just check that. Yep. And you only need these life estimates to 2 figures. For B, then what happens is this number goes down so it's just 90%. Point 377. And this is 95,000 cycles. So you have things are very sensitive to the load, you know, for these steels, okay, in general, in metals and practice. And so what we had here was we had a 10% drop in load, and you got 3 times the life. Actually, it could have been more than that. This goes down to 61. If it had gone down below 50, we would have had indefinite life. Okay, but let's assume they both stay in the high cycle region, which is a common thing. Then here we've got a factor of 3. Here's a common rule of thumb, conservative rule of thumb used in practice. But doing these calculations, it's not something you're going to do in your head, okay? And so here's a common rule when you're trying to estimate the effects of load, on life of load. Drop the load by 10%, you double life, okay? Okay. So if you drop it twice, 2 times by 10%, you got 4 times the life. Okay? I personally had an experience of using that. My wife has some things called Harrington rods in her back. They straighten up spine, have scoliosis of the spine, they straighten the spine up. And after a number of years, her rods had broken. The people designing those rods initially, it's extremely difficult to know what the loads are inserted in somebody's back. Once you've got some failed rods, and I went online and looked and found other people's failed rates, then I can get the life. Okay? Then we just redesigned it, so we dropped it by 20%. The life was typically minimum, I recollect, 8 years, maximum about 20. So, you know, on average, 14 years, but minimum 8. If you multiply even 8 by 4, and this is a conservative rule, then you get 32 years, which is pretty good. And we could easily drop the stress by 20%. Now, eventually you want people to go test these things and find out, you know, you test them and you test them, the existing ones, and you get their life, and then you test the new design rods and you test it. You don't just rely on a rule of thumb. But if you want to redesign something like quickly to get increased life, you use this rule, and you're almost certainly being conservative. And quite often, you know, if you things are designed for people's lives and you get a factor of 4, that's going to be enough. Okay? In fact, they have adopted that design of that Harrington rod now in practice. And so, but it takes more. This was just a preliminary design I did with a student. And but it should be done more consistently and carefully by testing. When you do that, because this is conservative, you actually find that the life increased more like a factor of 10, okay, which would be 3 times 3. But, so there's a handy rule when you see something that's hasn't got enough life, it's not too bad, and you want to double it, just drop the loads by 10% if you can, for steel. Okay. All right, we'll take a 5-minute break and then I'll go through. Are there any questions on this? Okay, there's a bit of data fitting here. Just use these formulas. You don't have to derive them. Okay, just use the formulas we've got here, and that's what you use here. When you get up in practice, they'll have their own formulas. They'll have slightly different numbers. They'll know their steels better. I'm just doing a generic steel here. Okay, but this will show you how to use fatigue life calculation, hopefully. Okay, we'll take a break for 5 minutes, then I'll go through the test.
Dr. Sinclair?
Yes.
I'm sorry. What's that last line on part B? Is it W goes to N times 3?
N divided by 3. Oh, sorry, poorly written. N went down by a factor of 3. So it was 28,000. N increased. Yes, it should be times 3. Sorry. Yes, thank you. Yes, I dropped it by 10%, and N goes to 3. Yes. 3 times this is 84. Okay, so it's more than 3. Okay. And here's the rule we just use is double. Yeah, that's my mistake. Thank you.
Thank you.
Now, we'll find ways to adapt this more test to other more complicated situations, but it turns out that bending is the dominant thing that breaks things because it oscillates, whereas torque doesn't. Torque yields things more quickly than bending because it's got shear stress, but that's a yield failure. But the fatigue bending is the dominant thing. Okay, let's break for 5 minutes. All right, let me start through test 2. The first 4 problems are about contact stresses, 1-point problems. When you have something like this, then the steel is wrapping around the aluminum and expanding the contact radius. What you're going to do is you subtract, you have 1 upon RA for the aluminum minus 1 upon RS to the minus 1. When you put the minus sign in here, this makes it smaller. When you take the reciprocal, it makes it bigger. If, on the other hand, the steel had been bound this way, that would be going away from contact. Then you take a plus sign here, and you make this bigger. Then we take the reciprocal, you make R smaller. Because the reciprocal, perhaps it's not always obvious the way it works. But you need a minus sign. If you didn't put a minus sign here, but you put it here, that's okay. Okay, you called 1 upon RA, 1 upon RS, and then you put RS as minus 50. Okay, you have to turn the diameters into radii, and you get 33.3. So this is a basic concept in contact mechanics, to know when the different radii are expanding the contact region because they're increasing R, that'll increase the contact, or they're reducing it because they're getting away from it. If you have any questions, just ask them. The Young's modulus, you could have put, it's the sum of the reciprocal of the contact moduli. The contact moduli have a 1 minus nu squared up there. Since it's up there both and the minus 1, I just put it outside, but you could put it up there, it doesn't matter. You could even put 1 minus nu a squared plus 1 minus nu s squared. Either way, it doesn't matter. That's a Poisson's ratio effect. It makes E star bigger, okay? Makes it a bit stiffer because of pushing in from the side. But when you have 2 things together, this reciprocal, these 2, sum of the reciprocal, is going to be a bigger number because they're 2. So when you take the reciprocal, this will reduce this and make the thing softer. So the Poisson's ratio here is 0.3, 1 minus 0.3 squared. It's going to be outside. Okay, that's going to make it bigger. Okay. But 1 upon 72 plus 1 upon 207 is going to make it smaller until you get 58.7. If you put these in GPA, the answer will be in GPA. You can give this answer in meters. Actually, that would be fine. You could give this in MPA or PA if you like. Okay, we haven't stuck to the strict SI rules that these numbers are supposed to be less than 1,000, but that's what they're supposed to be. The force was given to you as 100 kilonewtons per meter. So the length is irrelevant, or if you say the length is 1, okay, and the width of the contact region. This is the formula. All the way through, half a point for the formula, half a point for executing and getting the right answer. Okay. And so this is 4, this is F. I put the 1 in there if you like, you don't have to. The radius, now it's in meters, 0.03 recurring, and divide by 58.7. This has got 1,000. This has got 10 to the 9 when you put it. So together, then this is going to be 1 upon 10 to the 6. Okay. If I take the square root, I get 1,000. If I multiply by 1,000, I get millimeters. And so these numbers cancel and you get 0.269, but you asked for the width, so you have to double it. And the easiest formula to use to get the peak compressor stress after you compute a day is this, although there is another formula which you could use. Okay. I didn't write that down, but it's 4 upon pi times the average. Okay, the average would be F upon 2AL. Some of you remember it that way, which is fine. 4 upon pi, F upon 2AL is the same as this formula. And you substitute the numbers and you get 237 megapascals. This problem was arguably the most difficult of the 1-point problems. If I was preparing my formula sheet, I'd have written down a formula like this. If you didn't, and you had to derive it from equating the stress F over pi d squared upon 4 to SB, which will give you an E over L upon rho squared, and you have to remember that rho is D upon 4. Then if you started to derive it, we gave you some credit, even if you didn't get to here. If you got to here, you got 1 point. Okay. But it seems to me in designing for this test that I would write down a formula like this so I didn't have to derive it. In this case, then you just implement it. This is going to be in meters, okay? This force F is 100 kilonewtons. I put that all in newtons. Then I put E in pascals. And then this thing's going to come out in meters initially. And if I multiply by 1,000, I'll get the 36.8 millimeters. Again, you could have given this as 0.0368 meters. Okay, you could give some more decimal places. It just takes you time to write them. 3 figures is plenty. This is standard sort of thing. You subject a cylindrical shaft to a torque, then the maximum shear stress, constant all the way around the rim, is 16T upon pi d cubed. Okay. This is 250 foot-pounds, so you've got to convert that to inch-pounds. And then this will be in PSI, and I chose to use KSI, but you're welcome to use PSI. Okay. Now, to get the safety factor, this is brittle. It's SU upon sigma 1, okay, where this is the peak principal stress. When you just have tau T, then sigma 1 is sigma A plus or minus tau T. Tau T is tau max. There's no bending here. And so sigma 1 does equal tau T, so you get 2.6. Again, for a safety factor, you just need 2 figures. But you can give extra figures that you wouldn't be marked off for doing extra figures. The plate is subject to biaxial tension. I will post these solutions later today, okay, this afternoon. The plate is subject to biaxial tension, as shown, 40 in each direction. Okay. What's the safety factor against yield? We can do this one of 2 ways. I've said all along, Tresca is fine with me. Okay, it's more fashionable to use von Mises, but when I'm doing consulting, I can do Tresca pretty much in my head more easily than I can do von Mises. So I typically use this unless the people want von Mises. This works perfectly well. So it's SY upon 2 upon tau max. Tau max is not 0 here, it's 0 in that plane, but the outer plane stress is sigma 3, which is 0. So it's a half of that. And so this is 0, sigma 1 is 40, so it's 20, so you get 3. On the other hand, you could use von Mises, SY upon sigma E. This has got sigma 1 equal to 0, so sigma E is calculated by sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. These are all equal, so these 2 cancel, and you just get sigma 1, which is 40, 120, 40, you get 3. You get the same safety factor. As far as I'm concerned, if you had got different, the Tresca would have been lower and more conservative, and therefore quite acceptable. Now, you subject the face to a further 40 KSI. What's the safety factor? Well, now it's a half sigma 1 minus sigma 3. Sigma 3 is minus 40. 40 minus 40 is 80. You divide by 2, that's 40. So that's 60 over 40, you get 1.5. To do von Mises, either which is acceptable. You have these different sums. These 2 are equal, so it's 0, but this is going to be 40 minus 40, which is 80 squared. Minus 40, minus 40, minus 80 squared. So 280 squared. Divide by 2 is 80 squared. So sigma is 80. 80 divided by 120 is 1.5. You get the same answer. But, you know, for future reference in a final, for example, if you're asked to get safety factors against yielding, you can use either of these. Okay? It's what I said in class. That's it for the short answers. There's a simply supported beam of length L. Here's a free body diagram. Free body diagram, we've got to remove the supports and replace them with forces. The usual force I put on first is W. Some of you put WL in the center here. for some problems, that's equivalent, but it's not going to be equivalent here, so that's wrong. Okay, you're going to get the wrong bending moment and everything else. Don't do that. Okay, but so the applied load is W all the way across. There's a support here which you were told to call R backwards, so you just put that in as R. You could put RA equal to RB right from the get-go from symmetry. There's nothing wrong with that. Or you can put them not necessarily equal like this. Okay. You don't have any moments here. These are simple supports. That's an error. Okay. There's only with 1 point you start making an error, you don't get anything. You've got to get these free body diagrams right to solve these sort of problems. It's key. Then you can say RA equals RB by symmetry, or you can take moments about the center here and their moment arms are the same and you find they're equal. Or you can just look at it. Okay. Then if you sum the forces vertically, you get 2RA plus R equals W, then you divide by 2, you get WL, sorry, you get RA equals RB is WL upon R. This was simple enough. If you just wrote down the answer, that was fine. The next thing you have to do is determine the bending moment throughout the beam. Now this is key that you've got to be able to do this. Now, when you're starting off, sometimes takes a wee while to get comfortable with what forces are and how they act. And it takes a little bit longer to get what bending moments are. Okay, but you've got to practice enough so you get this stuff. So here's a bending moment diagram for X between 0 and L upon 2. Okay. This is X. I put the shear force in, but it's not going to matter. I'm always going to take moments about this end. Okay. M is positive compression at the top of the beam in our system. Okay. So it's the sum of the moments that go in that way. The first of those moments is this reaction, which you just figured out, 1/2 WL minus R times X. Then this thing here has a force in the center, effectively, of WX, and so its moment arm is X upon 2, so it's WX squared upon 2. That's why some of you perhaps start putting WL upon 2 up here in the free body drive. The other way you can do it is by integration. But when it's a uniform load, you can simply replace it by its magnitude and put that in the center. Okay, and that will be true for this. Okay. You can simplify this a little bit. You didn't have to. This answer is fine. But if you group them with the R term over here, then this will be a minus Rx, and then this will be WXL minus X, okay, which is a parabola. Then here's the bending moment once you get past the central reaction. It's exactly what you had before, plus now this is opposing R times X minus L upon 2. So these two terms are exactly the same as here. This is the additional term due to the R, and this is its moment arm, is X minus L upon 2. And if you simplify this, the only thing that's changed is R. This part stays the same. That's actually from a beam without R. And then this becomes, there's a plus Rx here, minus a half Rx here. So it's plus a half, this minus a half Rx, minus RL upon 2. Which is what you would have got if you come from the other end. Okay. So that's critical. You're going to solve problems in engineering to be able to do these. Now, the next part asked you to put in the bending stiffness and go ahead and set the problem up. Okay. So this is it here. This is my moment for the first part of the beam. Okay. There are 4 parts to this problem. It's worth 3 points, so there are 3/4 each. Okay. If you just put, you didn't quite get this right, you still got some credit for this. You had the EI at the bottom, stuff like that. Okay. But there's a bit of a carryover if you didn't get the moment right. You're certainly not going to solve the problem correctly. Then you're supposed to do it on the first half. So you're going to have delta equals 0 at X equals 0 and at the center. And then because it's symmetric, it has to look like this. There's 0 slope there. Okay. So if you started writing down some conditions over here and you wrote down correct ones, you didn't get any extra points, okay? You don't want to use a scattergun approach to answering these questions. If you wrote down something that was wrong, you lost 3/4 of the point. So you said the slope was 0 here, then even if you had other correct conditions, you lost 3/4 of a point for that. That's not true, okay? So these are the 3 you need, and you need 3. Why do you need 3? Because it's a second order ordinary differential equation. You have to integrate it twice, and you've got an unknown statically indeterminate problem. Okay. Now you want to work out the reflections using the table, which we just use superposition. If you didn't use superposition, then that's what you had to do here to get any credit. Just checking to see if you can do superposition, not something else. That's quite a lot easier to do superposition than anything else. Here's the 2 deflections. This is going to be R. This is going to be W. So you match them. And a lot of stuff cancels. The EI cancels. L cubed cancels. And you get WL would be the right units. It'd be 5. And 48 into 384 goes 8. So it's 5/8. So it's very easy to do this with superposition. The last problem here was the occasional tough 1-point question on these exams. This is a little more difficult to do. The maximum moment's at the center. Without support, you could actually get it. You wrote, without the support, it's just this and this. This is a parabola, it has a maximum at the center. You substitute, you're going to get WL squared upon 8. When you get the maximum moment from something like this, for that matter, you get the same thing here. This thing here, this any moment distribution looks like this. So it's a little bit questionable. You know, it's nothing here. A little bit questionable is the maximum here or here, okay? And you could look at the value in about the middle here. It's going to be bigger in the middle, okay? And that, but it's still nonetheless 1/4. So you get a 75% reduction in stress with the extra support. Okay. Any questions on this so far? I'll talk about administration of the test a little bit more in a moment. Here, this is a bit like a statically indeterminate problem you had for a column. You've just matched deflections. So you match the twist of the inner part is T1L, common L, G1J1, and the max the outside part is T2L, G2J2. You're not given diameters, so there's no real point in switching these J's in terms of diameters. Once you get that, then you want to get T1. So find T2 in terms of T1. Just multiply across by G2, J2, and you get this. Okay. Then when you add the torques to get T, you substitute for T2 and rearrange, you get T1 is G1J1 over G1J1 plus G2J2 times T. Okay. First part asks you, this is a cracked plate, okay? The safety factor 2, what's the maximum stress that requires the net section yield criteria? Net section yield means that the nominal stress through here, which is 1 minus 2C upon W times the stress here, it's bigger. And so this will go down by 1 minus 2C upon W. And then SY divided by N, that turns out to be 97.7 KSI. You have a number of things you have to do here to apply fraction mechanics. First of all, you have to decide whether it's thick or thin. This is the T star. If you get bigger than T star, you're thick. If you get less than T star, you're thin. And T star is 2.5 times K1C thick over SY squared. And this case turns out to be 0.144. This is a quarter of an inch thick plate, so it's actually thick. You might think a quarter of an inch compared to 10 inches is a factor of 40. That's not what you're comparing with. You're comparing with material properties when you make this. So this is a thick plate. So you have to use this K1C thick. Then you might decide, well, what about edge effects? Well, in this case, T is a half, W is 10, so this is pi upon 20. Okay, if you divide 180 by 20, you get 9 degrees, and you get 1.04 to 1.00. It was okay if you just said that C upon W was that's what did I say, less than a sixth or something like that, that you can just ignore this. If you stated that, like if you just chose it to equal to 1 without any justification, you lost a point. But you could have said what I said in class. So then you go ahead and calculate this. You get the thick, divide by n, divide by root pi times c, which is a half, and you get 20.7. And then obviously you pick the smaller one. That's what you could apply to this. Are there any questions on these solutions?
Dr. Sinclair, I had a quick question about 3A.
Sure.
So the question asked for the torque on the inner cylinder.
Yes.
So why wouldn't that just be that the answer that do you have for T2? Why wouldn't you just stop there? Why are you plugging in back for the overall torque and adding them?
Sorry. What you know is the torque T, the total torque T. That's what you know. Okay. And so should we give me an answer in terms of something else I don't know? That's not the answer.
Gotcha.
Okay. So it's very similar. You had a homework problem where you had a composite cylinder under compression load P, and you had to find out how it was sheared. That's what you have to do with these statically engineered problems. And then once you've got these T1 and T2 in terms of applied torque, you can figure out what the stress is. Okay?
All right. Sounds good. Thanks.
Sure. Any other questions about the solution? Let me give you some administrative details. Mohammed, who I think you call him, I call him Mohammed. Okay, he'll be available today from 2 to 6 and 10 to 12 Tuesday to pick up the test. His room is something like 37, something or other. Okay, it's in the handout anyway. Now, there are a couple of, I will have office hours. If you have questions about your grading, I would suggest that the most likely error we've made is perhaps not adding them correctly. We get the partial scores and get the sum. We can miss a partial score, and it's possible we didn't add the total scores correctly. Okay. You are now in a position to assess how you're doing. You can just use the absolute gradient system. You've got 2 tests. Okay, you've got an idea of what you're doing in the homework and attendance, and so you can assess your grade in the course as of now. That grading system remains the same as I gave out in the first day of class. There are a couple of other things. We had several students hand in papers without their name on it. Okay, as of now, your score is 0. Okay, so you better go get these tests. And I think there were 2 of you who, when you handed in the test, you had it enlarged so much that we couldn't grade it. Okay, there are very few, and so you need to see that, and we'll talk about what we're going to do with you with respect to this test. I also been given to understand that one of the proctors didn't give the last 15 minutes of the exam. I will investigate this further and we'll make adjustments. In the meantime, if you're in that group, okay, there are about 20 in that group, and you handed in your homework after 9:45, between 9:45 and 10, if you send me your name and the time when you handed it in, you'll be able to get some further credit because the proctor made a mistake. That's my understanding. I've got to talk to him, but that's my understanding is he cut it off at the time when you had your hand stuff in, when I've forgotten his name. He's not the TA for the course. Mohammed, Dr. Gautreaux and I proctored the 3 section, he's the other proctor. And so we'll make some sort of adjustment for that situation. Okay, are there any questions now about the test? If you have any concerns about your grading, then you need to get them to me by tomorrow. We're going to wrap this up, okay? And so feel free to look it over, and I will post those work solutions early this afternoon, and you can look them over. Just what we went through today would be no different. And there are some alternative methods to doing this. I didn't write down every alternative. I think I wrote down what I thought was the obvious alternative, stress reversal by measles. But there may be some other methods here too that I didn't bother writing down. But that's okay. Okay then. Well, I'll hear from some of you tomorrow. Otherwise, we'll see you on Wednesday. Good day.